In this video, we're going to talk about moment of inertia. The moment of inertia is an equation that helps us understand a shape's resistance to bending. Now, some of the equations we've talked about, for example, stress or yield strength, rely on or are compared against materials properties. The moment of inertia is applied to a purely geometry and is independent of material properties. So there's an equation for a circular shape and a rectangular shape, and certainly you can get more complex. You can break it down, for example, if you had like an I-beam, something that looked like that. You could calculate what that moment of inertia is. We're not going to do it. We're going to keep it pretty simple here. We're just going to look at a rectangle and a circle. And our equations there are, let's see, let's put rectangle up here, and circle there. So rectangle is BH cubed over 12. And our circle is pi d to the fourth over 64. Now, if we were to draw a cantilevered beam, so we've got a wall or something here, and we've got a beam that extends out, and we were to place a load at the end of it, this beam would probably deflect a little bit. So maybe it starts looking something like that. The area moment of inertia would help us understand how far that beam would deflect, or the resistance to that deflection. You actually have to use the moment of inertia in conjunction with another formula to actually calculate the actual deflection, but the moment of inertia is going to tell us how resistant this shape is to deflecting. And so let's I'll also mention that what we're talking about now is the area moment of inertia. There's also what's called the polar moment of inertia. The area moment of inertia is a shape's resistance to bending, while the polar moment of inertia is a shape's resistance to torsion, or being not rotated, but well, if you had a shaft and you hold one end of the shaft fixed and you try to turn the other end of the shaft, that would be the polar moment of inertia. So we're not trying to put anything under torsion. We're just doing bending, and so the area moment of inertia is what we're going to use. And the reason that we're covering this and not the polar moment of inertia is because thinking back over the past 15 years, I honestly can't remember even one example when I had to calculate the polar moment of inertia. Certainly there are times when engineers do have to calculate this. I'm just saying that it is far more common, in my experience anyway, to have to calculate the area moment of inertia. So we're going to do that. And again, this is not going to give us any definitive values in terms of how far something is deflecting. That will require integrating this, the moment of inertia, into a deflection equation, which we'll do, but not in this particular video. This is just going to give us a number that represents the higher the number is, the more resistance to bending there is, and the lower the number is, the less resistance to bending there is. So, with that said, let's work on one of these problems here. Let's say that the cross section of our beam here is rectangular. So I'm just going to draw in blue here a little rectangle, just to represent that if we were to look at a cross section of this beam, so in other words, if we were to look at a cross section right here and flip that, we would see this blue rectangle. And let's bring this blue rectangle down, just draw it a little bit bigger, put some some annotations on it. Let's say that our base is is the element of that shape that is like perpendicular to the direction with which force is applied, and so we're applying force down in that direction. So our force is applied like this, and so this is going to be our base, and then the height is perpendicular to that, and so here this is our height right here. So if we have a rectangle that looks like this, and we want to calculate the moment of inertia, let's just say that maybe our height equals, I don't know, our height equals 3 and our base equals 5. Could be inches, could be meters, doesn't really matter for for this exercise. The equation is bh cubed over 12, so it's going to be 5 times 3 cubed over 12. Now, it's really important to look at this exponent here, the cubed, right there. That exponentially increases the value of our height. So instead of 3, it becomes 3 times 3 times 3, which is 27. So we end up with 5 times 27 over 12. So you can see that the height has a huge impact in terms of the moment of inertia value. In other words, the height plays a much larger role in a shape's resistance to bending than the base does, right? Because the base doesn't have any exponent associated with it. The base is just the base. 5 times 27 over 12, that the actual number doesn't even matter really, but we'll just say 5 times 27 over 12, and that equals 11.25. So our moment of inertia for this is 11.25. Now, what's really interesting here is, let's say that our our shape was rotated 90 degrees. So now it looks like this. And now our base equals 3, and our height equals 5. Now remember what we just said about the exponent, right? That gives much more weight or value to the height value or amount than the base has. So now if we do this equation again bh cubed over 12, but now b is 3 and our h is 5, so we have 3 times 5 cubed over 12. So 5 times 5 times 5, that's equals 3 times 125 over 12. So if we calculate that, 3 times 125 divided by 12, 31.25 equals 31.25. So we have the same exact shape, the same amount of material as we had before. The volume of this, or the area, the shape, has not changed at all. All we've done is rotated it 90 degrees, and you'll see that if we compare this moment of inertia to the first one, 31.25 to 11.25, let's see, 31.25 divided by 11.25, our new moment of inertia is 2.78 times higher than 2.78, I'll just put an X, times higher than it was before, which means that this shape is going to be 2.78 times more resistant to bending than this shape will be, or in other words, it will deflect 2.78 times less. Now that's a big deal because we didn't really change anything. All we did is rotated the shape, and you can prove that to yourself by getting, for example, a piece of cardboard. If you had a piece of cardboard that looks kind of like this, right? And you hold it at this end. So you're, pinch it with your fingers and hold it over there, and then push down right here. That piece of cardboard is just gonna flop down really easily, right? But if you change it so your cardboard now looks like that, and again, you're gonna hold it down, fixed on that end, you're gonna push down over here, that piece of cardboard is gonna be a lot more difficult to deflect in the downward direction, right? And that all has to do with the moment of inertia. That's the power of the moment of inertia. The same is true for the circular cross section. We could do all this math again for the circular cross section, but it's really the same exercise, just using an equation that's specific to a circular cross section instead of a rectangular cross section. With a circle, there is no B or an H, there's just a diameter. But you can see that the larger that diameter is, it really has a huge exponential effect on the moment of inertia, right? If we double our diameter, it doesn't just double the moment of inertia, right? If we have d to the fourth versus 2d to the fourth, that's going to be, well, let's put some numbers in there. Let's say d is 1 inch, right? So, well, let's say d is 2 inches. D to the fourth is going to be 2 times 2 times 2 times 2, which is 2, 4, 8, 16, right? So it would be 16. And if we say we're going to double our diameters, now our diameter is 4, that's going to be 4, 16, what is that? 256, I think. 256. Let's see. Check my math there. 4 times 4 times 4 times 4. Yeah, 256. So by doubling our diameter, we have increased our moment of inertia by, I don't know what that is, 8 times maybe? 256 divided by 16 divided by 16? 16 times, is that right? 16 times 16? Yeah. So we have made our rod 16 times more resistant to bending than it was before, simply by doubling the size of the diameter. So pay attention to these exponents because they have a huge effect on how the moment of inertia turns out and how the shapes resisting to bending results. If you found this content helpful, consider enrolling in our signature program at mypipelineacademy.com. Whether you're an individual interested in beginning a new career as a mechanical designer or a company interested in training your new engineering hires, our signature program helps students develop the practical skills they need to be productive mechanical design engineers. Seating is limited. We hope to see you there soon.